So let's then try to think about this topic. Symmetry and quantum mechanics. There are very deep connections between these two. Very beautiful mathematical connections, but also in terms of what it really teaches us about how the world around us is put together. I'm sure you've often heard that symmetry really is the basis of quantum mechanics and particle theory, for example. It also plays a very important role in condensed matter physics and solid state physics. Now, this is our first time we're touching on this subject, so I can't give in this introductory course a complete treatment of the subject, but at the very least we can work through this particular example of a particular type of symmetry, but think about it, as this is the first one we're coming across, but to try to think about it in somewhat of a general way. So we're going to think about this particular symmetry, and this kind of symmetry is actually called parity. So the example is going to be parity symmetry. And parity symmetry refers to what happens when I think about my functions, say f of x, that describe my physical system, and then I map them onto f of minus x. And there are two ways to think about this. You can either think that I've taken all of my functions and flipped them around backwards, right? So I've basically physically taken my system and sort of inverted it. X goes to minus x, looking at it, if you will, in a mirror, right? Or I can think of it as a more of a mathematical exercise in terms of just asking myself the question, what happens if I change my choice of direction for my x-axis? Those are two very different ways of looking at this type of a symmetry. Now, as we continue to think about what parity might mean, the first thing that I'd like you to notice is that I've got this sort of general map that takes me from a function to a new function. And in quantum mechanics, of course, what we call a map that always takes us from a function to a new function as an operator. So associated with any symmetry, and in particular we're focusing on an example of this parity symmetry, there is an associated symmetry operator. So the parity operator for us then is going to be defined as an operator, which I will call capital P for parity. The hat tells me it's an operator, and when it applies to any function f of x, the result is defined to be just f of minus x. So the job of this operator is to go into my function, and anywhere it finds an x, it flips the sign on that x. That's why I say it's equivalent to just changing your choice of direction for the x-axis. Now, if we want to put a little column over here of general considerations, so in general, right, there's going to be some type of operation, It might be not just that changing the coordinate system where x goes to minus x. It could be a rotation, right? If I have, for example, an atom, the potential that the nucleus creates is spherically symmetric. And if I have spherical symmetry, there's a set of operations, namely known as rotations, that correspond to that symmetry. Just like this choice in x-axis has this, the symmetry that x goes to minus x has this operation of just flipping the sign on x. So in general, there's going to be some operation that corresponds to the symmetry, and there will also be some kind of an associated operator that we could devise that affects that type of operation that corresponds to our symmetry. Now, what I want to do before we begin to think just, again, very generally about generic symmetry operators and their properties, let's spend just a little time studying the parity operator. And it's, so this is actually, should say parity operator, right? And the properties, there are a whole interesting series of the parity operator. The most important for us are going to be the following. When I take this operator and I square it and apply it to a function, something very interesting happens. Now, as we move on in quantum mechanics, because at this point, once we had solved that finite square well, we've really covered everything that there is. You have the entire formal theory at your fingertips now. You know how to find bound states for systems. You know, of course, we've done a long segment on how you handle scattering states for the systems. And you also know what to do with these wave functions once you get them. Right? You know how to, given a wave function, by transforming to a different representation, you know how to predict the probabilities for any type of an experiment. By using the appropriate operators, you know how to test for pure states. You know how to calculate appropriate quantum mechanical averages given the bound and scattering states that you know how to calculate. And finally, you also know how to study time evolution by attaching complex exponentials to your wave function. So you know quite a lot now. What's going to happen in the course as we move forward is now that you have all of that basics, you have all the formal theory, we're going to be developing. The rest of advanced quantum mechanics really is nothing other than a development of a set of mathematical tools and techniques, such as the algebra that goes along with operators, a set of tools and techniques that actually just make finding the answers more convenient and more quick for us. So we're going to begin to learn to think a little more in terms of algebra on our operators. Very good. So